Hello there, everyone. We are ME Team 37, and our senior design project for this year has been focusing on a wind control device for high performance powerboats for Outer Limits offshore powerboats located in Bristol, Rhode Island. This is our senior design team. From left to right, we have Jonathan Denman, Sean Quinlan, myself, Ryan McCarthy, and Mai Nguyen. Outer Limits has tasked our team with designing a feature that will reduce the buffeting of wind felt by rear passengers on the SC-37 speedboat. This is a catamaran model, and for those unfamiliar with boating terms, catamaran means that there are twin hulls in parallel with an open tunnel of air underneath. According to the sponsor, on initial test runs with the boat, rear passengers were subjected to turbulent winds so strong that if you were to hold a phone up to try and record, it would fly out of your hand. The boat currently has a top speed of 125 miles per hour, and the buffeting of wind is claimed to be turbulent at speeds between 80 and 125 miles per hour. The sponsor initially wanted this feature to be retractable and transparent, but upon further talks, they are fine with it being a removable adjustment that can stow away easily when not in use. On this slide, you'll see some initial computational fluid dynamics, or CFD for short, we ran on a 2D cross-section of the boat. We decided to run the simulation of the boat at 3 different speeds to verify the sponsor's claims regarding wind buffeting in the rear passenger section of the boat, which is circled above. At 50 miles per hour, we found that wind speeds were not turbulent in the rear passenger seat area, which can be highlighted by the dark blue color seen, the blue representing a low air velocity value of roughly 18 miles per hour. At a boat speed of 80 miles per hour, we start to see the move towards some turbulent air as the rear seat passengers have now transitioned to a lighter blue shade, indicating an increase in the velocity of air, roughly equivalent to 30 miles per hour. Now, when the boat is running at a full speed of 120 miles per hour, the rear seat passengers are now subjected to a light blue, some green shade of air velocity, roughly equating to 6 to 8 miles per hour. For reference, the typical hurricane has a wind speed of 30 to 70 miles per hour. Suffice to say, the sponsor's claim regarding wind buffeting was proven, and our group now has an estimate of where we expect the air to flow over the boat when designing our new feature.
Alright, so here are our possible design prototypes that we came up with. We created numerous design prototypes to serve as the wind control device for this project. The design ideas that we came up with include the virtual windshield, the air cap, the rear barrier, and the airfoil roof. These designs went through a handful of iterations over time to get to where they are today. And the designs pictured here are what we both tested in our ANSYS CFD simulations, and were also 3D printed using ABS filament. And we tested them in the wind tunnel here on campus, in the Air Labs educational wind tunnel. All of these design ideas were modular, so they could be either used standalone or in combination with each other. And later in this presentation, we will reveal which wind control device that we decided was the most effective and ended up using as our final design.
In this slide, you can see the CFD simulations for the wind control devices that we designed. In the top left is the 50 mile an hour simulation for our rear barrier design, and it shows a decrease in wind velocity in the rear cockpit. But in the top right, you can see that the wind velocity decreases by a good amount, but still the passengers would see an average velocity of 30 to 40 miles per hour. In the bottom left, you can see our airfoil roof design, which has the advantage of being placed in different placements fore and aft, and shows overall decreases in wind velocity for the passengers, but so does not do as good of a job at 120 miles per hour as we would like, although there is an overall decrease in cabin wind velocities.
So here's the experimental analysis of the wind control devices. These 2 videos are a qualitative analysis inside the Aerolabs instructional wind tunnel in the Castleman workshop here at UConn. The video pictured on the left shows our baseline analysis of the scale model boat inside the wind tunnel without any wind control devices on it. The video on the right shows our analysis of the scale model boat with our wind control devices attached to the boat. And in both experiments, we attached yarn to several different locations on the boat model to qualitatively interpret where the main areas of turbulence are and see flow lines. Since this boat model is 1/40th scale, we were unable to get accurate results from this qualitative analysis, since we would have needed to increase the velocity in the tunnel by an unreasonable amount. But we were still able to get some valuable information from this. It's just not entirely accurate, and The real life boat has a maximum top speed of 125 miles an hour, which would have required us to have a wind tunnel capable of doing over 500 miles an hour, which would be totally absurd. And the wind tunnel that we had access to had a maximum speed of 145 miles an hour, which was nowhere close to this. But yeah, as I said before, we were able to gain some valuable information from this and complemented our CFD findings very well.
Although we are unable to currently confirm the effectiveness of our wind control device in the wind tunnel due to the issues involved with the matching random number and need to achieve the supersonic speeds, we are able to conclude that the airfoil roof is the best design idea. The airfoil roof will be mounted above the rear passenger's head and have the ability to rotate to change the pitch, as well as having the height adjustment and the linear adjustment toward the bow and stern of the vessel. The entire wind control device will also be able to deconstruct and tow away in the rear store locker of the boat. This ensures that the maximum comfort can be achieved for the passenger no matter shape, size, or the height because of the reflectability of the positioning. And that's all for today. Thank you for watching.